Hello and welcome to Some Assembly Required. This is the third video of implementing the rotate left absolute addressing mode opcode 2E. In the first video, we've collected the information we needed and wrote the test plan. In the second video, we've implemented the body of the operation. And in this video, all we have to do is update the flags. Should be easy unless we run into unexpected problems. But we're not done. The reason we're not done is because the status value is incorrect. Remember, we wanted the carry to be set at this point because we shifted out a bit. 9.4 has bit 7 set and we shifted it left, so it should have been in the carry. So we need to fix that, but before we fix that, we have to ask ourselves a more important question, which is, why did the test pass if the command is incomplete? So instead of fixing that, let's first fix the test. The concept of writing the test first, having it fail because the feature is not yet implemented, and then write the implementation is called test-driven development, or TDD. So let's look at the command we're executing. We want a command here instead of this no operation that will test whether the carry is set. And that's simple enough, just branch carry set. Where should we branch to? Well, we can branch anywhere. The next instruction will not be executed. So let's put here a break, and let's put here the no operation that signifies the end. So this is EA. Branch carry set is 2 bytes, so this will be 083F, and this will be 0840. The opcode for branch carry set is B0, and the address to jump to is calculated relative to the address of the next instruction. So the next instruction is at 083F, and we want to execute 0840, so we need to write here 1. And like I said, let's put here the break command, which is 00. Of course, once we have updated the test program, we also need to update the test plan. So this is the no operation, and that's not what we're going to do now. Instead, we're going to execute a branch instruction. And it's easiest here to copy from somewhere else we use the same instruction. Here it is. This is treated as an implied operand instruction. Number of cycles to execute is a bit complicated. We'll see that in a second. We run in branch carry set and we expect the branch to be taken. If we look at how many cycles that takes, this is the program counter relative. And it says it takes 2 instructions with footnotes 1 and 2. 1 talks about page boundary, which doesn't happen in our case. And 2 says that if the branch is taken, we need 1 more cycle. So since the branch will be taken here, that's 3 cycles. It is read from 083D, I think. Let's verify that. Yes. And the last read is the program counter of the instruction immediately following. Let's verify that with the simulator. So we want the set carry command, which is 38, followed by the branch carry set, which is B0, and we want to say 01. And we expect to jump here. We jump over the break to this command. Let's reset, and here we go. Set carry, cycle 1, cycle 2, and the carry is set. branch carry set, cycle 1 from 1, cycle 2 from 2, cycle 3 from 3, and then the next cycle is from 4. So that's the skip. So the last cycle always reads from where the next instruction after the branch is, even if we're branching. So that in our case, that will be 8, 3, D, E, F. And of course, the next command is our no operation read from 4, 0. So that's the test plan. Let's see if the plan plans out. I'm sorry, horrible pun. Sorry about that. Run, and we're asserting because opcode shorter than expected, which makes sense. The reason it makes sense is because we did not take the branch. We can see that this is the branch carry set. This is the address to jump to, and immediately the sync goes high, which means that the next instruction starts, which means that we did not branch. If we branched, it would take 3 cycles rather than 2, which makes sense because we didn't implement it. So now that we have a test that's failing, let's fix the code so that the test will pass. Test-driven development. Looking at the ALU, we see the status out. Status out is the ALU's opinion on what the flags are at the end of the operation. Of course, those don't matter unless we do something with them. Those go into this muxer, which goes into the status register. So there are 2 things we need to do. First of all, we need the state to tell the status register to take the data in. It can go from either the data bus or from the ALU status. So we need to tell it to go from the ALU status. And we need to tell it to update the carry flag. And you will notice that update C obviously comes from the decoder. So going back to the instruction decoder, the ALU bus results are available at the end of this cycle. So we need to set the control lines in this cycle. So let's look again at which control lines we need. We need the control signal for update carry. Control signals. And the control signals are defined here. We want to say stat update C. Gets a 1. And we want to tell the ALU, we want to tell the status register to take its inputs from the ALU results. So if we look here, we want the status inputs to be status source ALU. Looking at the decoder, this is called status source. So we're saying status source equals if all goes well, this should fix the test. Let's see if that's the case. Switch to simulation, reload so that our code changes take effect. And assert fails. Let's see why. Last access data incorrect. What is the last access data? It's a write. Our data out is 2.9, where it should have been 2.8. So let's see why that broke. And that's the value of test-driven development. We thought we finished that, but we broke something we've already had working. But we we're automatically notified about that. That's a very strong protection. So it is now a new day, and I think I know why the problem happened. It's more difficult to figure out how to solve it. So to recap, we're trying to rotate left 9-4 with the carry clear, and we expect to see 2-8 as the output, and instead we're seeing 2-9. And what we see is that the data bus gets loaded with 2-9, and therefore data out on the rising edge of the clock gets loaded with 2-9. But the reason the data bus gets loaded with 2-9 is because we say that the data source is from the ALU latch. And the ALU latch is taken from the ALU result, and we see that we're latching the wrong value. And the reason we're latching the wrong, it starts out as the right value, and this line is an asynchronous line, so it does not wait for a clock of any type. And it starts out with the right value, and then it switches to the wrong value at this point. And we see that the reason it switches to the wrong value is because the carry in, which is a line going into the ALU, gets shifted from 0 to 1. And that makes sense because what we see here is that the status value switches from F4 to F5. So what happens is that the carry gets set at this point. What we're seeing here is this command taking effect. We told it to take the carry from the ALU result carry, and since the ALU shifted a bit into the carry, we're actually telling it to take the carry flag from the ALU result carry. And since the number we gave it had the bit 7 set, after the rotate, the carry is set, and the carry is set in the status register. So that's actually doing the right thing, except it doing it at the wrong time. Which means that I thought I was done setting the timings for everything, and it appears that I am not, because it's not entirely clear how to solve this. So we did run into unexpected problems. Who'd have thought? The next segment is edited a bit differently than what I usually do. Usually I try the editing to be as tight as possible. You really don't need to hear me say and think out loud and all of those pauses while I think what to say next. The following segment is a little different because I thought there's a value in showing you the thinking process I went through. The problem we encountered here was one I was not expecting. I really was expecting the structure of the CPU to be done by this point. So I needed to make a change to the structure, and I wasn't sure what change I was going to do. The timeline here at the bottom, as well as if you click that button over there, has chapters. And you can just click on the next chapter and skip me rambling on camera about what I should do and thinking out loud. If you do want to watch it, here it is. I think the best solution is to play around with when things happen, when values get latched. I mentioned in a different video that where I'm latching values is not the same as where at least the MOS 6502 latched values. But I think that's too radical of a change to do at this point. I will do it later when I have when I've organized the test bench a little better, the test program actually. But right now it's a bit risky to do it. So let's see if we can solve it by adding something simple, preferably adding more flip-flops, which are cheap to me, and not more control lines, which are much more expensive. So let's have a look at the schematics. As you probably noticed, I changed the scaling of Vivado a little so that things will be clearer on the video. This is the ALU, and this is the carry-in line. What I'm thinking is, if I add a flip-flop here, latching the carry-in input, and doing so on the falling edge of the clock, that might solve my problem without introducing incompatibility with other commands. That's especially true since we've just added the line that takes we've just added this line, the line that takes the carry from the status. Up until now, everything was latched on the falling edge. So we can't do that on the falling edge. We can latch here. If we latch the value on the falling edge here, what that means is that we're setting the carry in based on the status value here. Since the status register updates on the rising edge, latching it carry in on the input on the falling edge will take the right value and make sure it's valid throughout the cycle. So yes, that's what we are going to do, as they say, under protest. That's not a very good solution, but it will work for our case. It will not add new control lines. And in fact, it will only add a single flip-flop. So I'll leave it with it for now. When I finish implementing all the opcodes, I'll go over the entire design again. And I'm pretty sure we can do something which is smarter than what I've done this time. So for now, let's just add a flip-flop on the input to this mixer, and that should solve the problem. Let's look for the ALU, and we're looking for the carry in. Here's the definition of the ALU, or rather, here's the introduction of the ALU into the CPU. And we see that carry in comes from ALU carry inputs. So searching for that, we're taking ALU carry inputs from status value flags carry. Instead, let's introduce a new variable called flags carry latched. And we're looking for the falling edge always block. So this block runs or latches on the falling edge of the clock. That's the neg edge. So what we need to do here is say ALU flags carry latched gets assigned the carry flag. If all goes well, this should solve our problem. Let's see. Go back to the simulator, recompile, and run. And we have a successful run. Let's manually check. This is the rotate left opcode. And we see that on cycle, this is 0, 1, 2, 3, 4. We read the 9-4 here. We process it in the ALU here to be 2-8. We see that it is 2-8. The carry in is low throughout the cycle. And here we write 2-8. And we do that. Let's look at the status value. Yeah, the carry gets set. So this command is executing properly. The next command is the branch carry set. And we see that it takes 3 cycles. And it jumps to 840. Yeah, so we aligned here. We got the carry flag sorted out. But we're not done. Because if we go back to the opcode and look at rotate left, we see that we need to set the carry flag, but we also need to set the 0 and the negative flag. For the most part, updating the negative and 0 flags is no more difficult than updating the carry flag. All we really have to do is just ask to do it. Done. But the 0 flag is a little more complicated. The 6502 did something very clever with the placement of the flags. The negative flag is on bit 7 and the overflow flag is on bit 6. What this means is that if our value is negative, all we have to do is to copy bit 7 from the data to the flag. And often the same goes for the overflow flag. The 0 flag is a little more complicated because it's not actually copying the data, but a calculation over the data, whether all the bits are 0. What this means is that updating the 0 flag is a bit more nuanced than just update. If we update the 0 flag, we have 3 options. We either preserve the old value, or we use the data, which means that we just copy whatever we get in the data into the flag, or we calculate, which means that we're asking whether the data is equal 0, and that's a bug. Probably not a serious one, but still. Of course, in our case, we do want to actually copy the data, so that's the flag we want. This value needs to go here into the status 0ctl. And essentially we're done. We've just updated the flags. We just need to run the simulation to make sure that we did this correctly. Here we go. This is the negative flag. And as promised, it indeed forgot how those are named. And we can see that it goes low at the same time that the carry goes high. So that seems to work. All right, we're almost done. Almost. One more thing to do. If we go to the datasheet again and look at the pin out, we see here a pin called MLB. Now, the B means that it's active low, so the pin's name is actually ML. ML stands for memory lock. The memory lock, MLB output, may be used to ensure the integrity of read, modify, write instructions in the multiprocessor system. Memory lock indicates the need to defer arbitration of the bus cycle when the MLB is low. Memory lock is low during the last 3 cycles of arithmetic shift left, decrement, increment, logical shift right, rotate left, rotate right, and I don't remember what TRB is. Test and reset memory address, and test and set memory address. So during the last 3 cycles of these commands, including rotate left, we need to set the MLB low. That's actually pretty simple to do. Going back to the code, the MLB here will be set by what we do here. So in order to set the last 3 cycles, we need 1, 2, 3. The line is called external ML. Inside the code, I'm using a different notation. Instead of saying B, I'm doing uppercase for those that are active low. So RW means that high is read, low is write. ML in uppercase means it's active low. So all we have to do is say gets a 0, and we need to say it at these 3 locations. Remember, it takes effect the next cycle. So this takes effect during this cycle. So this will set it low for the last 3 cycles of the command. In order to test that in operation, we need to actually see The ML line is visible in our simulation here. So let's reset and run. And we have a successful run. And we see that C7F4, 1, 2. So this is 1 cycle, 2 cycle, 3 cycles. And it is low for the duration. So that's that. There's just 2 things left to do in order to call this command complete. The first is to check the changes into the Git repository. So those are all the changes. Seems pretty good. So git commit opcode 2e rotate left absolute. So with that out of the way, there is just one thing left to do. Just one, but it's probably the most important one. 2e rotate left absolute. Done. Doesn't that feel good? We're done. Don't get me wrong, it was nice while it lasted, but it's good to be over. Rotate left is implemented. Yay. Next video will be moving to a completely different subject. It will be part 4 of 3, implementing the rotate left. What? Thank you for watching. Please like. Thank you for watching. Who wrote this?